So the next thing we should discuss in this module is storage. So data storage, I want to talk about the building blocks of data storage, which are the file system, object storage, database, data lake, and then what goes where in a kind of standard machine learning problem. And then also like where should we learn more about this. So the file system is the foundational layer of like any kind of storage. So the fundamental unit is a file, which can be a text file, a binary file, is usually not versioned at the file system level, and it's easily overwritten or deleted. And that can be as simple as just locally mounting a disk. So this is kind of this is what we're used to. This is what we have on our computers and usually on our network drives. We can network these file system drives such that multiple machines can essentially share a file system over the network. We can distribute the file system using stuff like Hadoop, which means that multiple machines can access files where they don't necessarily know where the file is physically. They just know it's on this distributed file system. So the file is somewhere in one of the machines, but we don't need to know exactly where it is. But at its foundational, it's still a file, right? So here, I think it's important to be mindful of access patterns, which means that if you have a single disk and all of your data is on that disk, and you want to read your whole data, then you're going to have to go through that whole disk. So that cannot be made parallel. But it can be fast. So whereas in object storage, which we'll talk about next, it's slightly different. So object storage is basically, I think of it as an API over the file system. So you can get a file, you can put a file, you can delete a file, and you kind of think of them as like API calls. And you don't necessarily worry where the actual files are. And you might actually, the fundamental unit is an object. So usually the object is binary. So it could be an image or a sound file. It could also be text. You could build in certain things that are nice, like versioning. You could build that into the service. So every time you put something to an address, you're not overwriting the file there. You're just adding another version of that file on top of it. You can build in redundancy to the service. So that means when you put a file to the object storage, it can get stored on like 3 different disks. But you don't necessarily care. You just want it to know that it's redundant. And this can be parallel because if stuff is on different disks and you make a whole bunch of GET requests, you can actually be reading from all these disks in parallel. But it's usually not fast because of this additional layer. And it usually has to support multiple people reading at the same time. So Amazon S3 is the canonical example of this. If this has been mysterious so far, like this is really just S3. But you can also set this kind of stuff up on-prem. So Ceph is what people use to do that. But object storage is pretty crucial to like modern day workflows. So databases are persistent, fast, and scalable storage systems and retrieval systems of structured data specifically. So the mental model that I like to have is that like basically you should think of the data being in RAM, so being like instantly accessible. But the database software makes sure that everything is going to get locked to disk, and even if the power is cut, nothing will get lost. So that's how I like to think of it. It's like joins are not going to be expensive because it's actually not going to seek on disk because everything should ideally be in RAM. But everything, if like I shut it down, then I can rest assured that everything is actually stored somewhere on disk. So the fundamental unit of databases is a row, which always has a unique ID of some sort, integer, can reference other rows, potentially in other database tables, and then you have values and columns. So this is not for binary data. So you should not store like a binary encoded string in a database, because the larger the database, the slower things is, the slower everything is, because it's all in RAM, basically. That should be your mental model. What you could do is you could store references. So for example, I have my images stored in S3, object storage, but I have the path to the image stored in my database. So in the database, I record who uploaded the image, how big the image is, the dimensions of the image, and the path to the binary file. The binary file itself is in object storage. And this is usually for data that is going to be accessed multiple times. So notably, this is not for logs. Logs are things that are generated as a service operates that you hope to not have to look at in the future, but you still want to store just in case you do have to look at them or you want to plot some metrics over them. So databases for stuff that you actually care about, not just kind of exhaust of your service operating. So Postgres is like the 2019 correct choice, like most of the time. Has really good SQL. It also supports unstructured JSON. So like when people were talking about NoSQL, they really meant being able to put a random JSON document without worrying about a schema of the database. But Postgres actually supports that. But it also supports SQL, so it's just a better thing. And it's very actively developed. So SQL, I want to call out as a specific thing that we should all care about because it really is the right interface for structured data. It's been around since, it's basically like a different way of programming. It's not what we're used to in Python, but it's a perfectly reasonable way to program data access. And if you are afraid of it and you avoid using it, then eventually you will just reinvent it, and it won't be as fast, and it won't be as complete. So I think a lot of people coming to data science from a non-SQL background are a little loath to like use it, but I don't think you should be. So data lake, maybe you heard that. So this usually refers to like an aggregation of data from multiple sources. So that could be your logs. It could be just maybe some service that you're running that just tracks when a user does something. And so it's usually called schema-on-read. So that means you don't worry about the schema as you dump things into the data lake, but then later you have a process for transforming it for needing to access it. So you kind of impose a schema on it as you read it instead of as you write it. In a database, you have a schema when you write. So here, yeah, data comes into the data lake, and then from the data lake, different things can perform different transforms and put it in either different databases or just package up a big file for training or whatever else you need to do. So Amazon Redshift is kind of the industry standard, I think, for this kind of stuff. You can send all these AWS services to Redshift and then query Redshift in nice ways. Snowflake is a startup that is very good also at doing the same. So what goes where, right? So binary data should be stored as objects and not necessarily files on the file system. I think they should be stored as objects because then you can version them. You can access them in parallel from all kinds of places you might want to train on. Metadata, so that would be labels about the binary data or things about user activity, if that's the business you're in. That should be stored in the database. So for example, maybe I'm working on a computer vision app, so I have a bunch of images. I store them in my object store, but as I label them, I store the labels in the database. So I would have the ID of the object and the label as a row in the database. If you need features that you didn't store in the database, for example, from like your user logs, then you can direct everything into a data lake, and then later you can set up a process to aggregate what you actually need. At training time, so that means like at the time that you will soon need a GPU when you actually start training, you copy the data that you need from all these sources onto the local file system or the network file system that your machine has access to. And the reason for that is you really want to minimize the distance between your data and the GPU. So you want the data, when you're ready to train, right next to the GPU. And where to learn more? There's a book called Designing Data-Intensive Applications, which I recommend. Kind of starts from first principles, like why do we have databases? How should we deal with logs? What is NoSQL? All this stuff, big data. So I recommend this book. You guys have questions?
There's a question about different sort of variants of SQL. So do you go for SQL or NoSQL or any of the other different variants that people are using these days?
Yeah, so like I said, I think Postgres is the right database because it's flexible enough for NoSQL applications, which basically means I can store JSON documents in Postgres, and then I can query in all kinds of crazy ways on those JSON documents. But I can also store schema documents in Postgres, and so it kind of works for both. So I would just use that. And then as for query languages, like I said, I think SQL is just like the standard, so I would just try to use that. And stuff like pandas. So pandas, makes a lot of sense for data scientists, But all that stuff makes even more sense after you kind of learn SQL. So how does merge work? What's it, what pivot tables? Like all that stuff. It's the mental model of SQL, right? Not of Python.
What are your opinions on feature stores, and when should you use them?
So a feature store would be, as you operate your service, some data gets generated, but you immediately transform it. You featurize it in some way, and then you store the features in a feature store. I think that, yeah, it's perfectly reasonable. So the alternative to that would be storing the raw data somewhere like in a data lake, and then later having a process that extracts the features that you need from it. But you could do it at the time that you actually store it. So it's kind of the same thing. Yeah?
I posed that question because the reason I'm asking the industry seems to have two different opinions. Netflix say definitely no feature stores, but Airbnb and Uber or Facebook, they all have feature stores. So I'm just curious to see where you stand on this.
So the questioner elaborated and said that Netflix favors feature stores, but
Netflix says no feature stores.
Netflix says no feature stores, but then Airbnb, Uber, and other companies use feature stores. There's a little disagreement about best practices. I personally like to start from as raw of data as possible, and then have a process by which you can obtain the final result. A feature store is something where at some point in the past, you've transformed raw data into some feature, and then at some point in the future, you will use that feature and train your model. But what if you change something about how you want to do the original transition between raw data and feature store, between when it was stored and when you decide to train? Well, if you do that, then you have to recompute. And so if some of your stuff is basically cached in a feature store, but some of your stuff you have to recompute because you've changed the featurization code, it's just mentally cleaner to always start from raw every time you train. So that is easier for me. But if you're at the scale of Airbnb or, I don't know what the constraints they have to work with are.
I want to add from my personal experience, what my experience is recommender engines, but Netflix, it has a relatively small number of items, like tens of thousands of movies and millions of customers. But if you take Amazon, it has millions of users and millions of items. So the compute feature here, it's really hard.
Yeah.
You can do it when you have 50,000 of movies. It's easy, but having millions of items and millions of users, it's not easy.
Yeah. I should also say, as we talk about these things, different people in the room have different areas of expertise and levels of expertise. And so we're not saying here at Full Stack Deep Learning that everyone should be an expert in all of these things that are little boxes on my landscape. But it's just, we should understand what they're about, but we don't necessarily all need expertise in every single part. And there's expertise that we'll never get unless we're working at the scale of some of these companies.